Okay friends, so we saw the governing differential equation for 3-dimensional continuum, homogeneous and isotropic elastic continuum. Uh, Initial governing differential equation is in terms of the force equilibrium. So, obviously it is in terms of the stresses and body forces and the second moment second rate of change of momentum or the so called inertia force. And once we take into account the generalized Hooke's law to relate stresses to strains, and then the definition of the strain components relating strains to different strain components to the deformation, we can transform the governing differential equation in terms of the deformations, and that governing differential equation in terms of deformation can be given in terms of a differential operator that relates strains to displacement L. So, L transpose D L u is the vector of deformations, plus F is the vector of body forces, distributed body forces along each component oriented along one each respective coordinate direction, and this is equal to the rate of change of momentum. So, that is essentially the statement of Newton's second law. The all the forces acting on the body, they are equal to rate of change of momentum of the body. So, this applies in the domain omega. So, our objective is we are looking to for finding an approximate solution. So, approximation uh, u hat as an approximation for u, v hat as an approximation for v, and w hat as an approximation for w. So, collectively we can refer to this as u hat, the vector u hat as an approximation to vector u. And when we substitute this approximation in the governing differential equation, that is what leads to the domain residual. So, the domain residual of the governing differential equation due to approximate solution is given by r omega is equal to L transpose d L. So, L is the familiar differential operator that we saw here. So, this is the differential operator which relates strains to uh, uh, displacements. So, L transpose D, D is the constitutive relation matrix, and L strain displacement operator, and u hat is the displacement, plus F the body forces minus rho u double dot. So, that is the second derivative of the displacement with respect to time. So, the accelerations, we are of course assuming that mass of the body does not change with time within the domain. So, this is the residual domain residual. So, now you may find the equivalence with the way we developed finite element formulation for one dimensional problem. The whole idea was find out what is the error in the approximation. If we are looking for an approximate solution, there will be some error in the governing differential equation, error of solution, error in the solution, and that error or residual is within the domain, it is to be minimized for getting a good quality of solution, and that is what we are trying to do here. We first estimate the residual or the error of approximation, and then we develop the statement of weighted residuals and develop the weak form of the statement of weighted residuals. So, this is the weighted residual statement. So, W is a weighting function. So, remember please note that r omega here that we are looking at is a vector, is a 3 rows, there are three relations in each coordinate direction. So, this is in a sense is a set of simultaneous differential equations. So, there are 3 differential equations, and here the residual that we are looking at are 3 residuals 3 equations. So, r omega x, r omega y, r omega z. So, along x direction, residual along x direction, residual along y direction, and residual along z direction. So, accordingly the weighting function also needs to be, there will be 3 weighting functions. So, W is a diagonal matrix. So, W I may say it, call it W x, W y, W z along the 3 diagonals, along the leading diagonal of this 3 by 3 matrix. So, this is what. So, transpose is something that I put intentionally, although for a diagonal matrix transpose really does not matter, W is same as transpose. So, W transpose r omega d omega. So, I substitute for r omega the residual. So, L transpose d L u hat, that is the first term of the residual, domain residual, and then the 2 terms W transpose f and rho W transpose u double dot, and they are all domain integrals. So, domain is a 3 dimensional domain. So, omega is a 3 dimensional domain enclosed by some boundaries in x y z space. So, it is a triple integral domain integral, and this is the complete weighted residual statement of weighted residual in the strong form. This is the strong form. Now, you may recall that it is first step towards a finite development of a finite element model is to develop the weak form of the weighted residual statement. The whole point of developing the weak form is that we need to look at the boundary term of the weak form in order to identify what are the primary variables of the problem and what are the secondary variables of the problem. So, we can consider this, look at the first term of this governing differential equation, and let me just take one row of the equation. This operator form is sometimes not so obvious to understand. So, let me just look at this first term of this equation. So, W x multiplied by del sigma x x by del x plus del tau y x by del y plus del tau z x by del z, right. So, these are all approximate stresses because they are derived from the approximate displacements. So, we look at only this term, particular term, just to make things illustrate the working, how we develop the weak form. Of course, the process is similar for each term. So, domain integral W x multiplied by del over del x, and sigma x x is of course proportional to d 1 1. So, that is the element of constitutive relation matrix multiplied by epsilon x x. So, sigma x x is equal to d 1 times epsilon x x. Epsilon x x is equal to del u hat over del x. So, that is the first term. So, domain integral of the first term of the residual of the first row. Now, this I can expand this, I mean you can look at it like this is equal to, if I define so, this is by using the chain rule of differentiation, I will have del W x by del x multiplied by d 1 del u hat by del x plus W x multiplied by del over del x d 1 1 right. And this term and this term, you look at these two terms, these are exactly identical. So, I can replace this term by this. So, essentially what this means is W x del over del x is equal to this total derivative of this product of these functions W x multiplied by d 11 del u hat over del x minus del W x over del x multiplied by d 11 del u hat over del x, right. So, when I substitute this in terms of this, so I get minus right. Now, this term can be converted into, this is a domain integral, this can be converted into a boundary integral by using Gauss theorem or divergence theorem in vector calculus, and you can this can be directly translated to, so 3-dimensional domain, it is enclosed by the boundary, 2-dimensional boundary, and it is derivative with respect to x. So, appropriately it will be n x d 11 d hat multiplied by W x. W x is a scalar. So, these are all scalar quantities gamma. So, this is what it looks like. So, d 11. So, this is what the boundary term looks like, and then second term is of course same. So, it is a domain integral del W x over del x d 11 del u hat over del x d omega. So, this is what you can refer to, you can understand this as 3-dimensional analog of integration by parts that we did in the problem 1-dimensional problems, by which we traded the derivatives from the residual term to the weighting function term, and that is what we have done here. So, the derivative term, this derivative from the residual term is transferred to the weighting function term, and then there is a boundary term here. That boundary term comes by invoking the Gauss theorem or Green's lemma, and this derivative, partial derivative with respect to x. So, the domain integral is transformed into this particular integrand multiplied by the respective direction cosine. So, if it is derivative with respect to x, so it will be the direction cosine with respect to x direction cosine of the outward unit normal. So, this we can do term by term. So, in this case for the second term it is derivative with respect to y. So, it will be n y in the similar term here. In third term it is derivative with respect to d z z direction. So, it will be n z in the third term here. So, we can continue with this term by term eventually, and then we get the governing differential equation. The weak form can be developed as this weighting function multiplied by the matrix of direction cosines. So, this is the matrix of direction cosines n x, n y, n z, and that multiplies with the stresses, stress component, stress vector, and this is boundary integral, and minus this is the domain integral. So, L W, so that is the differential operator from the stress terms is transferred to the differential operator on the residual term is transferred to the weighting function term, and then these are of course the domain integral with respect to forces and inertia term, and n hat is the direction cosine matrix transpose. So, that comes from the respective differential operator. What is the differential operator, and n x, n y, n z, these are the direction cosines of the unit normal. So, once we are done with that, now we look at the boundary conditions, look at the boundary term of this weak form. Now, looking at the boundary term of this weak form, we can see that this is the weighting function W. W is a 3 dimensional, it is a so W, I said this is a diagonal matrix of 3 weighting functions W x, W y, W z along the diagonals. So, it appears in its natural form on the boundary term without any derivative. So, that implies the primary variables are the unknowns of the problem. So, unknown problem is unknowns of this equation are u. So, the displacement. So, the primary variable of this problem are the displacements, and the multiplier here, these are the surface tractions. So, these are the tractions, strains, the stresses, stress components along the boundary. So, these are the stresses along the boundary. So, these are the corresponding secondary variables. So, that is what we do, identification of the boundary conditions. So, u is the primary variable vector. So, collectively I can refer to this as a u vector, all 3 displacement components, and t is the traction, and that is given by n hat transposed sigma. So, that is the vector form, and these are the secondary variables. If I look at the component wise, so u, that is the displacement along x direction, corresponding secondary variable is the traction or the forces along x direction. So, that would be sigma x x n x plus tau x y multiplied by n y and tau z x multiplied by n z. So, these are the surface tractions along x direction, and similarly for y and z. So, we have v and t y, w and t z corresponding pairs of primary variables and secondary variables, and together, as we mentioned earlier, we discussed earlier, primary variables and secondary variables, they will always come together in the boundary term. So, that it is always a work like quantity, it is always the work done by the secondary variable tractions in moving through the primary variables. So, now looking at the boundary term, we can infer that the approximate solution that we need to construct needs to be continuous in the primary variables, these are the displacements, with non-vanishing first derivative in the domain, because the domain integral that we have here, these involve first derivative of this approximation L u. L is a first order differential operator. So, this first order differential, so the first derivatives of the displacement approximation, they should exist. So, non-vanishing first order derivatives are required, and the element itself has to be C0 continuity, finite elements of C0 continuity, that is continuity of the 0th derivative of the primary variable across element boundaries are needed for discretization, exactly same as what the inference was from the boundary term for one dimensional problem. For two dimensional problem also it is the similar kind of inference that is drawn. The boundary term is just the weighting function. So, we substitute the unknowns of the problem in the weighting function term on the boundary term and we get the primary variables as u, v and w in place of w x, w y and w z. So, primary variable finite elements of C 0 continuity. So, that is the basic primary variables interpolation that is required to be continuous across the inter element boundaries, and the elements that we develop should have interpolation of these displacement components, suitable interpolation model for these displacement components while preserving this C 0 continuity. Now, how do we construct these elements? Now, this is the problem that we need to look at, because this domain omega needs to now be split into several subdomains, that is finite elements. So, suitable finite element approximation. So, in this case we of course develop the weak weighted residual and the weak form. Now, looking at this weak form, we identify the finite element model. Now, we will look at what kind of finite element would be suited. For example, one thing, for 3 dimensional, the domain is 3 dimensional. So, the element has to be a volume element, it has to enclose a volume. Now, the simplest regular figure which can enclose a finite volume is a tetrahedron with 4 vertices. So, that is the simplest finite element in 3 dimensions, 4 noded tetrahedron. 2 dimensional analog is the domain is an area domain, plane domain bounded by a curve. So, the simplest element that we will have in case of 2 dimensional problem should enclose an area, finite area, and the simplest element which can enclose finite area is a triangle. So, 3 noded triangle. So, 3 noded triangle in 2 dimension, 4 noded tetrahedron in 3 dimension. So, these are the simplest elements in 2 and 3 dimension, but of course, we can go further and develop other elements. For example, I can use a rectangle, 4 noded rectangle, that also encloses area in a 2 dimensional plane, and similarly analog of rectangle in 3 dimension is a cuboid, right. So, 8 noded cube. So, all vertices, and so that will enclose a volume. So, a tetrahedron, of course, triangle tetrahedron is one family of elements that we can develop. Then we can have another family of elements, rectangle and cube, and of course, there are other possibilities. We can have prism and I mean triangular prism, and or even wedge element so called. So, that will also be enclosing volume. So, its a cross section is a triangle, but it can be extended. So, it is a kind of a triangle wedge or prism, and that is also will enclose a volume. So, that can also be a valid finite element for 3 dimension, and so on. So, there are several possibilities, and we will see. Now, the formulation, the treatment of the finite element formulation remains the same. It now boils down to defining these respective elements which will satisfy these requirement. They have to enclose area, and they also have to ensure compatibility of the continuity of the approximation across the element boundaries. So, we will see how that is achieved, and once we take care, then all that remains is the basic interpolation model. How are the unknowns interpolated within the element in terms of primary variables of the nodes of interpolation defined at the nodes of interpolation, right. So, we will consider in our next lecture how these I mean now for a substantial portion of our engagement will be devoted to just this discussion of development of interpolation function for different element geometries, and subsequent analysis, subsequent plug-in into the finite element model would be straightforward. It is a standard process, right. So, in our next lecture we will simplify these 3-dimensional equations to 2-dimensional cases, because fewer terms to work with and the diagrams are easier to draw and easier to understand. So, the basic philosophy of finite element approximation is more easily understood when we discuss in 2 dimension. 3 dimensions bring in lot more complications of visualization. So, in our next lecture we will take the equations, similar equations for 2 dimensions, and then develop finite elements for 2 dimensions first and work out how things work out in different form. And from there again we go back, we will return to this discussion of 3-dimensional finite elements and see how the discussion of 2-dimensional finite elements can be extended to 3-dimensional finite elements in a straightforward seamless manner. Thank you.